All right, let's jump right in, folks. Today we're taking a deep dive into the world of hydraulic fracturing, specifically proppants and acid fracturing. We've got a mix of textbook excerpts and technical papers to unpack, so are you ready to get our hands dirty? Figuratively, of course.
Absolutely. Always up for a good deep dive.
Okay, awesome. So the goal here is to really grasp the science behind choosing the perfect proppant and how acid fracturing works, especially, compared to propped fracturing, which I think most of our listeners are probably pretty familiar with. Our sources kick things off talking about, well, the history of ceramic proppants. They weren't always the star of the show, were they?
Nope, not at all. Back in the day, sand was the go-to proppant. It was cheap, readily available, seemed like a good fit.
Yeah,
But as wells got deeper, especially in the 70s, sand just couldn't keep up.
I can imagine. The deeper you go, the more intense the pressure and temperature, right?
Yeah, exactly. Way down there, sand would basically get crushed, lose its ability to prop open those fractures. It's kind of like, well, if you're building a house on sand, it's not going to be very stable.
Makes sense. So you need a proppant that can withstand those extreme conditions. And that's where ceramic proppants stepped onto the scene.
Right. Our sources even mention a test at the King Ranch in Texas back in 1975. That was kind of their debut.
Wow, 1975, that's a while back. But okay, so they solved that crushing problem. But I'm looking at these pictures in our sources, and the difference between a good and bad proppant is pretty striking. Is it just about looks, or is there more to it?
Oh, it's definitely more than just looks. A good proppant has to have, well, a few key qualities. First, it needs high compressive strength, basically, so it doesn't crumble under pressure.
Yeah, like those super strong weightlifters, they don't buckle under pressure.
Uh-huh, exactly. Second, a good proppant should be uniform in size and shape, so you can pack it in nice and tight and create a permeable fracture.
So it's like building a solid wall with bricks that are all the same size.
Exactly. If you've got all different shapes and sizes, you end up with gaps and weak points.
Makes sense. And I'm guessing it needs to play nice with the formation fluids, too?
You got it. It has to be chemically inert so it doesn't react with the fluids down there.
Okay, so we've got these super tough ceramic proppants, but there are different types, right? Like high density, intermediate, lightweight.
Yeah, lots of options. It's about picking the right proppant for the specific well conditions.
So how do you even begin to choose? What are some of the key factors you'd consider?
Well, conductivity is a huge one. It's basically a measure of how easily oil and gas can flow through that propped fracture.
So higher conductivity means more oil and gas flowing out, which is what we want.
Exactly. Think of it like a highway system. A high conductivity fracture is like a wide, well-maintained highway, allowing traffic to flow smoothly. Low conductivity, it's like a dirt road full of potholes.
Ah, that makes perfect sense. A nice, smooth highway for those hydrocarbons to zoom through.
That's the goal. But there are a bunch of things that can mess with conductivity downhole, make things a lot trickier.
Oh, I bet. Our sources mention embedment as one culprit. What's that all about?
So embedment happens when the proppant actually gets pushed into the rock itself. That narrows the flow path, reduces conductivity.
Hmm.
Our sources even provide a formula to calculate width loss because of embedment.
So it's like parts of that highway suddenly shrinking down to one lane.
Exactly. That's going to cause a bottleneck.
Mhm.
And then there's the fluid used to carry the proppant downhole. That gel, it can leave behind residue, further reduces conductivity.
Ah, so it's like gunk building up on our highway, making it harder to drive. Anything else that can throw a wrench into things.
Oh, yeah. Time and temperature, those play a big role too. The conductivity of a proppant can decrease over time, especially in those high temperature environments downhole. Think of it like wear and tear on our highway, cracks appearing, potholes forming.
Wow, it's amazing how complex this gets. I mean, we're talking about a microscopic world down there, but it sounds like a whole ecosystem of its own.
It really is, and we're just scratching the surface here. Our sources also dive into some pretty technical stuff like non-Darcy and multiphase flow. Basically, recognizing that we're dealing with oil, gas, A&D water all mixed together.
Oh, right. It's not just one fluid down there, so that adds another layer of complexity.
It does. They all interact in these, well, complex ways that can further impact conductivity.
Okay, so choosing the right proppant is more than just picking the strongest one. You got to consider all these factors, the rock, the fluids, the temperature, even time.
Exactly. Our sources even provide an example of correcting standardized conductivity values to account for all those factors. Adjust for embedment, gel damage, and the mix of fluids. It's like, well, fine-tuning a recipe to get the perfect flavor.
So even with all this complexity, there are ways to make informed decisions about proppant selection. But it's not just about conductivity, right? There's also the matter of getting the proppant where it needs to go.
You're absolutely right. Proppant transport is key. We need to make sure it can travel downhole and, distribute evenly throughout the fracture.
And that's where proppant size comes in, right? Our sources mention something called Stokes' law. What's that all about?
Stokes' law describes how fast a particle settles in a fluid. Basically, the bigger the particle, the faster it settles.
Ah, okay. So if you're working with a deep well, you'd want smaller proppant particles, the ones that can travel further without settling out too early.
Exactly. And we can't forget about the perforation size either, those holes in the well casing. They need to be big enough for the proppant to pass through.
Right. If the holes are too small, the proppant's not going anywhere. So you've got the proppant moving downhole, it's the right size to get through the perforations, and it reaches the fracture. But how much proppant is enough?
Ah, that's the question of proppant concentration. You need enough to prop open the fracture, create a nice wide flow path, but not so much that it restricts the flow.
So it's like packing a suitcase. You want to fill it up, but not overstuff it to the point you can't close it.
That's a great analogy. And different proppants have different densities too,
Mm.
so that affects how much you need.
Oh, right. Denser proppants pack tighter. So you might need less of it to get the same level of support. It's like, well, packing a suitcase with clothes versus books.
Exactly. You'll need fewer books to fill the same space because they're denser.
This is a lot to consider. I'm starting to see why proppant selection is such a, well, a crucial part of hydraulic fracturing.
It's definitely not a one-size-fits-all situation. And our sources actually highlight some real-world examples, showing how factors like rock type, permeability, zone thickness, they all play a role in choosing the best proppant for the job.
Okay, so it really is like a chef carefully selecting ingredients and, adjusting a recipe to create the perfect dish. Each well is unique.
You got it. Now, while proppants are crucial in many cases, there's another approach to, well, stimulation we need to talk about, acid fracturing. What happens when you're dealing with rock formations that are a bit more stubborn, let's say?
Hmm, that sounds like a whole other set of challenges. I'm definitely ready to dive into that.
Welcome back to our deep dive.
All right, we've been unpacking proppants, all the things to think about. It's a lot. But I'm curious about acid fracturing. It feels like a totally different approach, to getting oil and gas flowing.
It is. Remember, with proppants, it's all about, physically holding open those fractures. But acid fracturing, it's about dissolving parts of the rock itself, creates those flow paths.
Oh, okay. So instead of like propping a door open, we're making a new door. But why would you choose acid over proppants? When does that make more sense?
Well, imagine you're dealing with a formation, and it's got a lot of carbonates, like limestone or dolomite. These types of rocks, they're really susceptible to being dissolved by acid.
Ah, so you're using the acid to like eat away at the rock and create those channels.
Yeah, exactly. It's kind of like using, a powerful drain cleaner to clear out a clogged pipe. You're dissolving the blockage to get things flowing again.
Okay, that makes sense. So it's like choosing the right tool for the job. You wouldn't use, drain cleaner on a greasy pan.
Exactly. Different tools for different situations. But it's
Yeah.
not like acid fracturing is magic bullet.
Hmm.
There are definitely things to consider before going down that path.
I bet. Our sources mention that the rock formation's reactivity to acid is a big one. What does that even mean?
So some rocks are more reactive to acid than others.
Yeah.
Carbonates, like we talked about, they react pretty readily.
Mhm.
Other rocks, well, they're barely affected. It's like, I don't know, pouring water on a sugar cube versus a rock.
Okay. The sugar cube will dissolve the rock, not so much.
Right. You need to know how acid soluble the rock is before you even think about using acid fracturing.
Mm-mm.
And permeability matters too.
Right, permeability. We talked about that with proppants too.
Yeah, permeability is all about how easily fluids can move through the rock. If it's low permeability, that acid might struggle to get in there and do its job.
So the acid needs some space to work its magic. What about natural fractures? We talked about those before. How do they factor in with acid?
Actually, natural fractures can be a real plus with acid fracturing. They give the acid like pre-existing pathways to flow and react.
Yeah.
Could really boost the treatment's effectiveness.
Oh, interesting. So they're like these natural highways for the acid to travel along. But I'm guessing there's more to it than just like pumping acid downhole, right? Our sources mention different acid fracturing techniques.
You're right. There's several techniques, each with its own, strengths and weaknesses. One of the classic ones is called pad acid fracturing. It's a two-step process. First, you create the fracture using a gelled fluid. Then you pump in the acid to etch the fracture faces.
Oh, so it's like prepping the surface before you really get to work.
Exactly. And our sources even give a real-world treatment schedule, like a recipe for a good pad acid treatment. Another technique is called whisper. It stands for widely spaced etched ridges.
Whisper, that sounds kind of cool.
It is.
Mm.
Especially in those uniform rocks like chalk. Whisper, it uses viscous fingering to make these evenly spaced etched ridges. Doesn't create one big fracture. It's more like a bunch of smaller ones.
Ah, okay, more like a network of channels instead of one big highway.
Yeah. And in some formations, that actually works better, provides better long-term conductivity.
Wow, who knew? I'm learning so much. Are there any other techniques we should know about?
One more I'll mention is closed fracture acidizing, CFA. This one's different. See, it's about etching the fracture after it closes, creates a rough, kind of grooved surface that helps with permeability.
So you're not holding it open, you're changing the surface itself to let fluids through.
Yeah, exactly. It's like creating tiny channels within the rock.
That's pretty amazing. Okay, so we've picked a technique, we're ready to go. But how do we make sure the acid actually, does its job effectively? Our sources talk about acid spending. What's that all about?
Acid spending is all about that chemical reaction between the acid and the rock. You want it to react, to make those flow paths, but you don't want it to spend too quickly either. There are two big things here, reaction rate and mass transport.
Okay, break those down for me. What are those exactly?
So reaction rate is how fast that acid reacts with the rock, like how quickly a fire burns. Mass transport is how fast the acid gets to the rock face, like how quickly those firefighters can deliver water to put out the fire.
Okay, I'm following you. So the acid needs to react at the right speed and reach the rock surface. What happens if one of those is off?
If the reaction rate's too fast, the acid might be used up before it gets deep into the formation. But if the mass transport is slow, it might not reach the target at all.
Ah, so it's all about balance, getting things just right. And now we get to the really interesting part. Our sources mention something called wormholing. It sounds a little creepy.
Yeah, it kind of does. But wormholing is really cool. It's how the acid etches these, intricate tunnel-like structures into the rock. It's like, if you could see it, a microscopic labyrinth.
Wow. So the acid's not just etching uniformly, it's creating these specific patterns.
Right. And the shape and size of those wormholes, well, it depends on a lot of things, like the type of acid, the reaction rate, fluid loss.
Fluid loss, right. That's how much fluid leaks off into the rock during the treatment.
Exactly. Too much fluid loss, well, it's like trying to water your plants with a leaky hose.
Yeah.
You're not going to get that water where you need it.
So you need to manage fluid loss to make sure the acid's etching the right spots. But our sources mention that predicting acid fracture conductivity is a real challenge. Why is that so hard to figure out?
It's a mix of things. The models we use, they're often based on, like, observations and data, not a perfect understanding of the physics and chemistry going on.
So even with all the science, there's still a bit of a guessing game.
Kinda, yeah. But that's what makes it fun, right?
Yeah.
Always more to learn. And then there's the whole world of additives that you can use in acid fracturing.
Oh, right. The secret ingredients.
Exactly. They can do all sorts of things, protect the equipment, boost the etching, control that fluid loss we talked about.
Like spices in a recipe. What are some of the key ones?
Corrosion inhibitors are big. Acid's
Yep.
corrosive, right?
Yeah.
Got to protect the equipment. So corrosion inhibitors, they basically create a barrier on the metal surfaces, stop the acid from eating them away.
Ah, so it's like armor for your tools. What else?
Surfactants are another one. They're multitaskers. Reduce surface tension, prevent emulsions, even help create foam. They make the acid work better, more efficient.
Okay, and what about controlling fluid loss? Any additives for that?
Yep. Gelled acid is one way. By making the acid thicker, you slow it down, less leaks off into the rock.
Oh, I see. It's like thickening a sauce with cornstarch, keeps it from running all over the place.
That's a good way to put it. And then there's retarded acid. It slows down the reaction rate, lets the acid get deeper before it gets used up.
So it has more time to work its magic. So we've got the acid, the additives, but now how do we get it to the right place? Our sources talk about placement and diversion.
Right. That's all about making sure that acid spreads out evenly, treats the whole target zone.
It's like making sure you water your whole garden, not just one little corner. So how do you do that?
There are a few ways. Packers, higher pumping rates, chemical diverters. But one of the coolest methods is ball sealers.
Ball sealers, what are those?
So ball sealers are these little balls, some rubber, some biodegradable, and you pump them down with the acid. They get lodged in the perforations, block off some of the flow, force the acid to go somewhere new.
Oh, I see. So it's like strategically blocking off some paths to make the acid go where you want it?
Exactly. Our sources even have a diagram of a ball catcher. It catches any balls that float back up during production. You don't want those floating around.
That's pretty clever. So with ball sealers, you can really fine-tune where that acid's going.
Yep. But you got to make sure you're using the right size balls, enough of them, and the right pumping rate. It's all about the details.
Okay, so we've got the acid, the additives, the diversion techniques. I'm starting to see the whole picture here. But I'm wondering, are there ever times when you use both Proppants and the acid, like in the same treatment?
Great question. And the answer is absolutely. Combining them can be a really powerful strategy, especially in those tough formations.
Interesting. So it's like using both a hammer and a screwdriver? Sometimes you need both to get the job done.
Exactly. Sometimes you might use acid first to, clear away minerals that are blocking flow, and then use Proppants to hold things open.
So it's a way to get the best of both worlds.
Right. Or in formations with high closure stress where proppants might struggle, the acid can give them a little help, like adding reinforcements to a structure.
It's a dynamic duo. But combining treatments, that's got to come with its own set of challenges, right?
Of course, timing's a big one. When do you pump each one? Does the acid go first or the proppants?
It's like baking a cake. You got to add things in the right order.
Right. It all depends on what you're trying to achieve and what the formation's like. Sometimes you want the acid to do its thing first. Other times the proppants go first.
Wow, this is so complex. There's so much science and engineering involved.
It is. And it's always evolving as we learn more about how to optimize these techniques.
And speaking of optimization, our sources point out that these combined treatments are especially valuable in unconventional reservoirs, those tight, low permeability formations. Why is that?
Well, unconventional reservoirs, they're tough. They need a bit more help to get things flowing. It's like they need multiple keys to unlock their potential.
So the acid and proppants work together to unlock those tough-to-reach resources.
Exactly. But it's not just about using them together. It's also about making them better. Researchers are constantly trying to develop new proptents, make them stronger, more durable, better suited for those specific conditions.
Like super proppants. And what about new acid systems? Anything exciting happening there?
Definitely. They're working on acids that are more targeted, more efficient. Imagine acids that can dissolve specific minerals, without damaging the rest of the formation. Or acids that you can activate on demand. Super precise control.
Wow, that sounds amazing. It seems like the possibilities are pretty much endless.
They really are. And as technology improves, we're going to get even better at, optimizing these treatments and getting the most out of our energy resources.
It's great to hear that. But of course, we can't talk about hydraulic fracturing without talking about the environment. It's a topic that always sparks a lot of discussion.
It's a crucial part of the conversation. And our sources do a good job of, highlighting the concerns and the progress being made to address them.
So I think it's time we dive into that next. Okay, so we're back for the final part of our deep dive. We've covered proppants, acid fracturing, the whole shebang. But now let's talk about, well, the environmental piece of the puzzle.
Yeah, it's a big one, no doubt.
Yeah.
And our sources do a good job of, laying out the concerns and the progress that's being made.
So where do we even begin? I mean, water usage is something I hear about all the time. Millions of gallons per... Well, that's going to have an impact, right?
It does use a lot of water, that's true.
Yeah.
But it's important to keep things in perspective. Compared to other industries, even some agricultural practices, the overall water footprint of hydraulic fracturing isn't that huge.
Okay, so it's not just about the total amount, it's about how it compares to other water uses.
Right, exactly. And the industry's working hard to reduce that footprint even further. Recycling produced water, the water that comes back up after the frac, that's becoming more and more common.
So reusing what they've already got, that makes sense.
Huh.
What about using, I don't know, different fluids, like those gels or foams we talked about?
Yeah, those are options too. Anything to reduce the amount of fresh water needed.
Okay, that's good to hear. But what about groundwater contamination? That's a big one, right? People worry that those fracking fluids could get into drinking water. How real of a concern is that?
It's a valid concern for sure, and something the industry takes very seriously. Our sources talk about the layers of protection that are in place to prevent that from happening.
Okay, so what are some of those safeguards?
Well, first of all, the well bore itself, it's built with steel casing and cement, creates a barrier between the well and the surrounding rock, like a shield to prevent leaks.
So it's like a fortress around the wellbore protecting the groundwater.
Yeah, that's a good way to put it. And then there's depth, too. Hydraulic fracturing usually happens way down thousands of feet below the surface, much deeper than most drinking water aquifers.
So there's a good amount of physical separation there, but how do we know those safeguards are actually working?
Well, there's a ton of monitoring. They test the groundwater before, during, and after fracking. They look for any changes that might signal a problem.
So it's not just about having the safeguards, it's about making sure they're doing their job. What about like the fracking fluids themselves? Are those changing to be, well, less risky?
Absolutely. They're always researching new, more environmentally friendly fluids.
Yeah.
Some of the harsher chemicals used in the past, they're being phased out.
So it's moving towards, cleaner and greener fracking fluids. That's good to hear. But what about induced seismicity? That's a scary one. Can fracking actually cause earthquakes?
It's complicated, to be honest. Our sources say there is a connection between fracking and, well, seismic activity, but only in certain places,
Yeah.
specific geological settings.
Okay, so how does that even work?
Most fracking operations, they don't cause any earthquakes you can even feel. But sometimes, the wastewater disposal, that can cause problems. If it's injected near a fault line, it can increase pressure, and that can lead to, well, small tremors.
So it's not the fracking itself, it's what happens to the wastewater afterwards.
Right, and even then, those earthquakes are usually tiny. Most of the time, you wouldn't even feel them at the surface.
Okay, so they're not like those massive earthquakes that cause damage, but it's still, kind of unnerving that human activity could be triggering them. What can be done about that?
We're doing a lot of research, trying to figure out the best ways to manage that wastewater. Choosing disposal sites carefully, avoiding fault lines, maybe even treating the wastewater so it can be used for something else.
So lots of efforts to, reduce that risk. It seems like when it comes to fracking and the environment, there's just so much to consider.
There is. It's not simple.
Yeah.
There are risks, for sure, but there are also a lot of efforts to minimize those risks and make the process safer.
And it sounds like the industry is, well, they're taking it seriously. They're not just ignoring these concerns.
No, not at all. There's a lot of research and innovation happening driven by both regulations and a real desire to do things the right way.
Well, that's good to hear. I mean, it's a complex issue, but it sounds like progress is being made.
Yeah, it's a journey, for sure. And it's going to take everyone working together, the industry, the regulators, the scientists, all of us, to make sure we're developing these resources responsibly.
Well said. So I think we've covered a lot of ground today. Proppants, acid fracturing, the environmental considerations. It's been a real deep dive.
It has lots of information to digest, but hopefully our listeners have a better understanding of this crucial technology.
It's amazing how much science and engineering goes into it, and it's constantly evolving, too.
Yeah, who knows what the future holds? Maybe even more exciting discoveries and advancements.
I'm sure there will be. Well, that's it for this deep dive. Thanks for joining us, and keep those brains buzzing.
See you next time.